Okay, today we want to talk about the definite integral, and it is essentially finding the area under a curve, only this time we need to take into account when the curve is above or below the x-axis. So let's just remember how we found area in the first place, just when we had a curve that was above the x-axis. So to find the area under a function y equals f of x on the closed bounded interval, remember we used the slice, approximate, refine method, and we spent quite a bit of time actually on each one of these parts. So the slice part was to find the area of a single rectangle, so the general ith rectangle. We found the area of that thing. So in order to find the area of a rectangle, we need to know what the width is, and we need to know what the height is. So in this case, when we use the right endpoint approximation, all of the widths were the same. So we used what is called a uniform partition, right? So all the widths were the same. And we got that just by taking the interval from A to B and dividing by the number of rectangles. So that broke that interval up into n equal parts, right? N subintervals of equal length. And so we called that number delta x. So that's the width of each rectangle. And then for the height, remember we could choose any point in the subinterval, but in this case we chose the right-hand endpoint and called it xi star, but that right-hand endpoint was a plus I delta x. Remember we drew a picture to see how to get this. If it was the left endpoint, it would have been a plus I minus 1 delta x. Or we could have used the midpoint. And later we'll look at any old partition with any old sample points. But for now, let's just recall what we did last time. So here's the height of each rectangle. And so the area of the rectangle is just the width times the height, right? So f of xi star, or f of a plus I delta x times delta x. And then for the approximation, what did we do? We added up the areas of all of the rectangles, right? So there were n rectangles, we find the area of each one, and then add all of those areas up. So that's this thing. That's what we called Rn. So this was the right endpoint approximation to the area under f. And that was just the width times the sum of the heights, right? We could factor out the width here because it was constant, right? They were all the same. So remember, we could just factor it out. And then the refined part is we get a better approximation the more rectangles that we have. And so we let the number of rectangles go to infinity, right? And that will hone in on the exact area. So now we want to define the definite integral, and it is essentially this same process. The only difference is we want to be able to define a sum using any old partition, and we want to be able to take any sample points in the subinterval from x sub I minus 1 to x sub I. Okay, before we can define the definite integral, we need to make sure we're clear on the notion of a partition. So exactly what is that? I think in the previous video we kind of defined what it is, but here it is again just in case. So if A to B is any closed interval, a partition of that closed interval is just a set of points, and we want to label them in such a way that x0 is the left endpoint and x sub n is the right endpoint. And we also want to write them down in such a way that they increase in size as the subscript increases, right? So we want a to be equal to x0, that should be less than x1, x1 is less than x2, blah, blah, blah. The general ith subinterval here, we want x sub I minus 1 to be less than x sub I, and then we want x sub n to be equal to b. And when you look at how these things are arranged on the line, so here's the closed interval from A to B, we are not demanding that these things are equally spaced. So we called that a uniform partition when they were equally spaced. Here we are not requiring that this partition be uniform. So it's like take some points and throw them down on a line, and then they fall wherever they fall, right? So we will call delta x sub I the length of the ith subinterval. So that's just the distance from here to here. And then we will define the norm, right? So this is called the norm. The norm of this particular partition is the largest subinterval length that shows up. So you look at delta x1, look at delta x2, delta x3, so on and so forth, right? And then pick the largest one of those that shows up. Now we're allowed to do that because there's only finitely many of these subintervals, right? There's n of them. So when we pick the largest one, we call that length the norm of the partition P. Okay, let's look at an example really quick. So here's a set of points called P. So 0, 1, 1.8, 2.9, and 4. And we're saying that this thing is in fact a partition. It's a candidate because, right, these numbers are all in increasing order. If this thing is a partition, what is the norm of P? Well, first of all, it's a partition of what? Well, you can look at the first and the last, and you can see that this must be a partition of the closed bounded interval from 0 to 4. And now, in order to find the norm of P, we need to find the lengths of each subinterval, right? So here's my x0, x1, x2, x3, and x4, right? So my first subinterval goes from x0 to x1, and then x1 to x2, so on and so forth. So delta x1 is the length of the first subinterval. So that's 1 minus 0, and that's just 1. Delta x2 is the length of the second subinterval, right? So we start at x1 and stop at x2. So that's 1.8 minus 1. And so here we get a 0.8. Delta x3, the length of the third subinterval, x3 minus x2, 2.9 minus 1.8. And so there we get a 1.1. And then the fourth subinterval, the length of the fourth subinterval, x4 minus x3, and so that's going to be 4 minus 2.9, so there again we get a 1.1. So we look at these four numbers and pick the largest that shows up in the list. Even though 1.1 shows up twice, it's still the largest in the list, and so the norm of P now is 1.1. So that would be a good final answer for this example.